I'm Qin Liu from Hong Kong Baptist University. I will present our work, Local Algorithms for Distance Generalized Call Decomposition over Large Dynamic Graphs. The identification of cohesive subgraphs is one of the major tasks for network analysis. Many models have been proposed to represent cohesive subgraphs, such as K-call, K-charts, maximal click. Recently, a new model called distance generalized call has been proposed. It is also known as KH call. In a KH call, every vertex has at least k vertices whose distance to V is at most h. For example, in the figure, the graph is a 4-2 call since every vertex has at least 4 one-hop and 2 hops neighbor. The KH call model has many applications, such as landmark selection, community search, graph coloring, and maximum H-club computation. Given a distance threshold h, KH call decomposition aims to compute the coordinates for each vertex. Here, the coordinates means the maximum k such that the vertex is in a KH call. The KH call decomposition can facilitate many applications. For example, we can use the coordinates to build indexes for community search. The state-of-the-art methods for KH call decomposition are peeling-based algorithms, which are to iteratively delete the vertices having the minimum h degree. But these algorithms suffer from two major limitations. First, the peeling-based algorithms have low parallelism. It is due to two reasons. First, the peeling-based algorithms need global graph information to find the minimum h-degree vertex for deletion. Second, the peeling-based algorithms work in a sequential manner. That is, the vertices are processed from low h-degree to high h-degree one after one. The second limitation of peeling-based algorithms is that they cannot support dynamic graphs efficiently. When graphs change by inserting or deleting nodes or edges, it is inefficient to update the coordinates by running a KH call decomposition algorithm from scratch. Motivated by this, we revisit the problem of KH call decomposition in our work. Given a graph G and a positive integer h, the KH call decomposition is to compute the coordinates for every vertex. Moreover, when the edges of graph G are inserted or deleted, it needs to update all vertices coordinates accordingly. To efficiently handle the KH call decomposition, we first introduce some theoretical basis. First, we introduce the h-index. Given a set of integers, the h-index is defined as the maximum value of k such that there exist at least k integers whose value is no smaller than k. For example, if the integer set contains 7 integers from 1 to 7, the h-index is 4 since 4 integers, that is 4, 5, 6, and 7 are no smaller than 4. Then we assume that each vertex of the graph is associated with an h-index, and we define the pairwise h-attainability index. Given two vertices u and v and a positive integer h, the pairwise h-attainability index of u with respect to v is the maximum of the minimum h-indexes for every path from u to v whose distance is no longer than h. For example, I try to compute the pairwise 3 attainability index of V3 with respect to V1. For V3, there exist 3 paths from V3 to V1, whose distance is no longer than 3, that is P1, P2, and P3. First, we compute the minimum H indexes for each path, which are 2, 2, and 5 respectively. Hence, the pairwise 3 attainability index of V3 with respect to V1 is the maximum of these 3 minimum H indexes, which is 5. Based on the attainability index, we define the n-order H index for a vertex. The n-order H index of vertex V is defined in two cases. When n equals 0, the vertex n order h index is its h degree. When n is greater than 0, the vertex n order h index is defined as the h index of its h neighbors n-1 order pairwise h attainability index. We take the vertex V1 as an example and assume that h equals 2. When n equals 0, the n-order h index of V1 is 4, since it has 4 one-hop and 2-hops neighbors, that is V2, V3, V5, and V6. When n equals 1, the n-order h index of V1 is the h index of V2, V3, V5, and V6 zero-order pairwise h attainability index, which is 4. For vertex n-order h index and its conies, we have the following theorem. When n is big enough, vertex n-order h index converges to its conies. This theorem lays a solid foundation for our algorithm design. Based on the theoretical basis just introduced, we present the algorithms for K-H-core decomposition. We first introduced the K-H-core decomposition algorithm in static graphs. The basic idea is to iteratively compute the n-order h index for all vertices until convergence. Finally, the n-order h index is the conies. In addition, we also propose 3 optimizations to speed up the basic algorithm. Moreover, we extend the algorithm to handle the K-H-core maintenance for dynamic graphs. Here, we want to highlight 3 differences from the static K-H-core decomposition algorithm. First, the initialization of zero-order h index is different. Second, we try to identify unaffected vertices to avoid n-order h index computation. Third, we utilize original conies for early termination. For details of the algorithms, please refer to our paper. Next, we present experimental results. We conduct experiments to evaluate the efficiency of our proposed algorithms. We use 18 different types of real-world data sets in our experiments. We first evaluated the convergence rate of all algorithms to see how fast each algorithm converges. We can observe that our algorithms converge very fast. For example, when h equals 2, at the 10th iteration, almost 97% of the vertices have converged for local algorithm. We next compare the efficiency performance of our method with the state-of-the-art algorithm. We can observe that our algorithm consistently outperforms the state-of-the-art algorithm by 1 to 3 orders of magnitude. Then we evaluated the efficiency of our proposed updating algorithms for K-H-core maintenance over dynamic graphs. Here, the local plus represents the method that performs K-H-core decomposition from scratch. We can observe that our proposed algorithm, dynamic update algorithms, that is EDA and EIA, are much faster than local plus, achieving 1 to 2 orders of magnitude of improvement. To conclude, in this paper, we first introduced 2 novel indexes. Second, we propose a parallelizable local algorithm for K-H-core decomposition. Third, we extend the local algorithm to handle K-H-core maintenance over dynamic graphs. Finally, experimental results demonstrate the efficiency of proposed algorithms. Thank you.